Hi, I want to talk about another special case of projectile motion, and with special case, it's about hiding information in a problem that's zero. And this problem is called zero change in height. So an example of zero change in height would be a goal kick in soccer, where the goalie kicks the ball and then it lands at some point downfield, because soccer's played on flat horizontal ground. Or throwing a baseball and catching the baseball at the exact same height that it was thrown. Or really any sort of projectile motion that you can think of that starts and ends at the exact same elevation. So as the name suggests, the zero is the total change in y. Delta y equals 0. Now, that doesn't necessarily mean that the object never leaves the ground, because otherwise it's not a projectile. But if we wanted to find our maximum change in y, our maximum height off the ground, we do have another hidden zero. The maximum distance above the ground occurs when the y component of velocity goes to 0. And we'll make use of that fact in just a little bit. So, some facts about this motion. Zero change in height, the motion is completely symmetric. So if you know the y component's initial velocity, the y component's final velocity is going to be minus that. If you know the initial angle above the horizon, then the angle below the horizon is going to be the same size. So theta initial equals minus theta final. And because the motion's symmetric, if you know the total time, then the time to get to the maximum point is going to be half the total time. And the maximum point is halfway between the two. So if we wanted to, we could think of an object sort of falling forward and backward in time in the first half and second half of its projectile motion. Now, depending on the information we have, then we can figure out what else we are able to solve for. If we have time and we have the distance that the object travels, that's enough information to actually figure out everything else about the problem. But what's customarily sort of given, or this case is presented as, is we have an initial speed for our projectile and we have a launch angle. So given that framework, let's look at the equations of motion for zero change in height. Now in the x direction, the only equation of motion is to say that our displacement in x, or in this case we call it the range, is equal to our speed in the x direction times time. And that's the only equation we have to deal with. Now, if we look in the y direction, with acceleration, the final component of our y velocity would be the initial component of our y velocity minus the strength of gravity times time, which often isn't very helpful because we aren't making use of our free piece of known information, our hidden zero. So if we then think about displacement, well, if I have initial velocity and time, 0, my displacement, is equal to my initial velocity in the y direction times time minus 1/2 times the strength of gravity times time squared. So what that means then is, if a minus b equals 0, v initial times time in the y direction equals 1/2 g times delta t squared. So I can cancel one of those delta t's from my acceleration term and cancel the delta t in my velocity term. So the initial y component of my velocity, which is just, from basic trig, the initial speed of the projectile times the sine of the launch angle, is going to have to equal 1/2 times the strength of gravity times the total time of flight. And then if we want that total time, we can multiply this by 2, divide it by g, and our total time would be 2 times the speed of the object times the sine of theta divided by the strength of gravity. And the time to get to our maximum height is just the speed times the sine of theta divided by the strength of gravity. So taking a look at this equation, the sine of theta is 0 at an angle of 0. So if the object is launched at an angle of 0 and it has 0 change in height, that means it's not a projectile. It doesn't spend any time in the air. Now, the sine of theta is maximized at a value of 1 when theta equals 90 degrees. Well, a 90-degree angle means we've taken all of our speed and redirected it straight up in the air. So if the object is completely moving upward when it's launched, then it's going to stay in the air for the longest amount of time. So let's take a look at the height that it's going to achieve. Well, we could calculate that height by saying that our velocity at y max is 0, and that'll be the final velocity for this problem. So our maximum possible height would have to be equal to 0 plus 1/2 times the strength of gravity times the time to y max squared. So time to y max squared gives me v squared times the sine squared of theta divided by the strength of gravity squared. When I multiply that by 1/2 and the strength of gravity, I cancel one of those factors of g in the denominator, and I get a maximum height that's equal to the initial speed squared divided by 2 times the strength of gravity times the sine squared of the launch angle. So again, the maximum height is 0 if the object isn't a projectile. If we put the object up in the air at a 90-degree angle, it's going to go to its maximum possible height because it has the most motion moving it upward. So the last piece is looking at this range from the perspective of knowing a launch angle and a launch speed. Well, my initial velocity in the x direction is just my initial speed times the cosine of my launch angle. And my time is 2 times that speed divided by the strength of gravity times the sine of my launch angle. So when I multiply my total time by my speed in the x direction, I get, again, an initial speed squared divided by the strength of gravity, but then I have 2 times the sine of theta times the cosine of theta. And from trig identities, sine theta times cosine theta is equal to the sine of 2 times the angle theta divided by 2. So that means then that my range would have to be equal to v initial squared divided by the strength of gravity times the sine of 2 times the launch angle. And here's something neat. This is a function that also has a symmetry built in about a launch angle of 45 degrees. We get our maximum value for sine at an argument of 90 degrees, so our launch angle is 45 degrees, so 0 change in height without air resistance tells us an object travels farthest at an angle of 45 degrees. Now if we go above or below that, the sine function has a corresponding value from any number from 0 up to 90, with a value from 90 up to 180 degrees. So what that means is, if you were to look at any possible angle that isn't 45 degrees, there would be another angle that would give you the exact same range, the exact same distance. So if your angle is 90 degrees, you spend all of your time going up and coming down, but because you have no speed in the x direction, you don't go anywhere. If you launch an object at an angle of 60 degrees, you go the exact same distance as an object launched at an angle of 30 degrees, but at 30 degrees, the object gets there sooner than at 60 degrees. So sometimes, like in sports, that can be a good thing or a bad thing. If you want to throw a quick pass, you throw it at a low angle so that it gets to the receiver quickly, but the downside is it's really easy for the defense to reach up and block it because it's not going to be very high off the ground. On the other hand, if you want to give people time to get down the field and either set up coverage or just be in a position to catch, If you throw it at an incredibly high angle, then it will take a lot longer to get to where it's going. It may not go as far, and then you have the advantage and disadvantage of having a long time to react. And there are many, many applications where you can use different trajectories as a way of seeing that objects from the same launcher end up at the exact same place at the exact same time by taking a high angle, long time, and a lower angle, short time. Thanks for watching.